So, very good afternoon to everyone. So, this is Surya Narayana from Department of Physics, IIT Hyderabad. So, today I am going to discuss about the conductance quantization and multi-bit memory devices that we have developed using the resistive random access memory. So, the prime material that we have used is the tantalum pentoxide. So, this is about our laboratory, magnetic materials and device physics laboratory, where we try to work on metal spintronics, then the mesoscopic physics and magnetic materials for the energy and devices, and I would like to acknowledge all of my students. So, so if you want me to classify our research areas, we try to work on quantum phenomena, where we try to realize the quantum transport in the form of the conductance quantization and tunneling phenomena. Then we also try to develop the devices for the cognitive technology. So, we try to develop the memoristic devices for the neuromorphic computing. Then we also try to work on this spintronics, where we try to deposit magnetic thin films and study their magnetic properties. So, the plan of the today's talk is I will give introduction about this conductance quantization and various ways by which we can realize this conductance quantization, and the primarily I would like to focus on the conductance quantization through the resistive random access memory devices, and also the conductance quantization through the mechanically controlled break junction devices. These are the two important experimental techniques that one can use to realize the conductance quantization and the tunneling phenomena. So, as we know that we have many technological devices, the spin electronic devices, nano electronic devices, MEMS and NEMS and bio-NEMS. Despite having all these devices, we are standing at the threshold of the electronics. So, as a result of this fact, we need to push the technology forward. The technology can be forwarded by having the different designs and architectures, and by having the better materials, and also by doing different kinds of experiments like using the STM tips and the single molecule magnet based transistors and multi-dot devices. And one can also use new principles, and one of the new principles that I am trying to propose is the quantum point contact devices, which we try to develop at our laboratory and try to realize the conductance quantization. The importance of this quantum point contact device is that one can realize the quantum transport through the point contacts, and one can also implement these new ideas in various applications. Okay. So, the point contact devices can be achieved by various ways. One is the mechanically controlled break junction devices, which is uncommon. Most of the time people try to use, people try to develop using the scanning tunneling microscope and so on. But here I try to show you that the conductance quantization has been realized using the mechanically controlled break junction devices. Another one is the scanning tunneling microscope, which generally people use. Then the electrochemical methods are also very famous techniques to realize the point contact devices and the memoristic devices. This is also another new evolution in realizing the point contact devices. So, this is the structure of the memoristic devices. I will try to brief you a little bit about these memoristic devices, and this is the working principle of the mechanically controlled break junction devices. So, basically, like you will have a flexible substrate on which one would keep the nanowire and then push this flexible substrate using a motor and piezo, so that the device, the nanowire will break exactly at the middle. So, it all depends upon how precisely you can control the gap between the two electrodes using piezo. You can actually control the gap between the two electrodes at the nanometer scale, up to 1 nanometer or 2 nanometer, so that one can realize the conductance quantization and also tunneling phenomena through the contacts. So, the conductance quantization, like if you look at the point contact devices, like the quantum transport can be achieved by having some equalities between various length scales. So, suppose if the width of this construction is of the order of the Fermi wavelength and the length is less than the mean free path, you can say that the transport is the quantum transport. So, such kind of constructions can be made, as I mentioned, like by different ways, using the scanning tunneling microscope, MCBJ, then memoristic devices. And as a result of these equalities, one can realize the voltage versus conductance with different steps. Okay, the one step is equal to 1 G naught, which is basically 2 v square by h. So now I would like to go to my research work where we have realized using the memory devices. As you know that we have many memory devices like volatile memories and non-volatile memories. The emerging non-volatile memories are FERAM, MRAM, PC RAM, STT RAM and RRAM. So here I would like to focus on the resistive random access memory. So the resistive random access memory, it is having many capabilities like one can write speed will be of the order of nanoseconds, read speed is of the order of nanoseconds, retention can be up to 10 years, the endurance can be up to 10 power 12 years and the write speed is of the order of microwatts. Okay, so the non-volatile memory, so it is having a very simple structure, metal insulator and metal structure, so through which like one can apply potential difference between the top electrode and the bottom electrode. And suppose depending upon the conducting filaments, you can classify this RRAM as VCM and CBRAM. Suppose if the conducting filaments that forms between the top electrode and bottom electrode is with the oxygen defects, you can call it as a valence change memory, and if the conducting channels are formed with metal ions, you can call it as the conductance bridge RRAM. Okay, so this can be a bipolar resistive switching and the unipolar resistive switching, and if two polarities are required to get the set switching and reset switching, you call it as a bipolar switching. And if you have to, if you require only one polarity to get the set and reset switching, it is called as the unipolar resistive switching. Then you can also have digital and analog switching depending upon how fast the current goes. So the tantalum pentoxide is very important material for the quantum applications and to realize the conductance quantization. So because it is having very high dielectric constant of the order of 25 and the wide band gap, so that it reduces the leakage currents, and so many oxygen vacancies will be there, so that oxygen defects will be there in the sample, because we wanted to develop the quantum device using the oxygen defects. So that's the reason why we selected tantalum pentoxide, and it is also compatible with the CMOS. Then the scalable to nanoscale, up to nanoscale one can develop these devices. So this is experimental techniques that we have used, like we tried to use the radio frequency sputtering technique to deposit these films. And the reason why we selected FTO and AZ as the top and bottom electrodes is because the work functions of these materials are almost similar, so that the efficient transfer of the electrons can happen. So this is X-ray diffraction pattern that we have obtained, like we could able to see the amorphous nature for the tantalum pentoxide. The XPS spectrum has been taken, so it actually gives tantalum peak as well as oxygen peak, and then the tantalum is in the 5+ state, and the oxygen, we could able to see two peaks for the oxygen. One is the lattice oxygen, another one is the non-lattice oxygen. Lattice oxygen is responsible for the tantalum and oxygen bonding, and the non-lattice oxygen is responsible for giving the defect based conducting channels. So as the non-lattice oxygen is also there, it is so much advantageous for our device applications. So we also tried to do the IV characteristics. What we could see is that we could see a bipolar resistive switching. Initially the device was at high resistance state. As we swept the voltage from 0 to positive voltage, the device has gone from high resistance state to low resistance state, and when we swept the voltage to the negative side, it has gone to low resistance state to high resistance state, and so on. It is not just that we tried to do one time, we have done these measurements for several cycles, up to 225 cycles, and we could able to see the reproducibility, which essentially shows the robustness of the device that we have developed. The endurance and retentivity characteristics also demonstrates that this device can be useful for the memory applications, and the on-off ratio is of the order of 200, which essentially demonstrates that one can easily distinguish the information between the 0 and 1. The most importantly, like the conduction mechanism, we try to explain using two ways. One is in the high resistance state, we could, depending upon the slopes that we have obtained, we assign this to space charge limited conduction, and in the low resistance state we assign to the ohmic conduction. And then as I mentioned, like this RM can be due to the oxygen defects or metal ions. To confirm whether it is due to the oxygen defects or metal ions, we try to measure the temperature versus resistance graph, and from the slopes that we have obtained, we confirm that the filaments are due to the oxygen defects. The slope that we have obtained is almost equal to the values that corresponds to the oxygen defects. Then this is the schematic diagram for the conduction channel mechanism that we have seen. Initially the device is at high resistance state, and as we swept the voltage, the conduction channels are formed. By controlling the voltage value in a precise way, one can get very fine conducting channels, and when we try to reverse the voltage, we could able to get the rupturing of the filament. So the conducting atomic force microscopy measurements also have been performed to confirm the conducting channels in the present device. Initially when we try to apply 0 volt, we don't see any voltage. As we keep increasing the voltage to the device, what we could see is that conducting channels. So these conducting channels and then the temperature dependent resistance graph. So all these experiments together confirms that our device is having the conducting channel model. So then further, the quantum conductance in RRAM devices through these conducting channels formed by the oxygen defects are realized by sweeping the voltage and the measured the conductance. So very well defined quantum conductance values are observed, and the quantized steps with integral and half integral multiples of G0 have been observed. So as these conductance values are very much stochastic in nature, we also try to do the statistical analysis by fitting with the Gaussian function. We try to get the standard deviation values. So what we could see from the statistical analysis is that the most probable conductance value is 2 G0, 2.5 G0 and 3 G0. And we also try to calculate the relative standard deviation by using this formula. So from the relative standard deviation values that we have obtained, we confirm that our device demonstrates the stable conductance quantized states that can easily be distinguished. So then we also try to calculate the current values using the Landau theory and try to match with the experimental realization. Using this formula, using the Landau theory, we try to calculate the current values, where NT and NB are the number of occupied subbands Sx from the top and the bottom side. So basically, like this is the experimentally conductance steps that we have obtained, and the blue lines are calculated from the theory. So these values exactly matches with the experimentally measured values, the theoretical values. So from this we confirm that there is a perfect correlation between the theory and experiments, and shows the multiples of integral and half integral quanta of the conductance. So then this device we also tried to use for the multi-bit memory characteristics. The experiment is as follows. So like we swept the voltage between the minus 0.5 volts and minus 3 volts with a step of 0.06. As you could see here, the conductance is from 0 to 18 G0, which is in the quantum limits. So at each and every step, we try to wait for 29 cycles. We could see the conductance plateaus. So the number of conductance plateaus that we have observed is 36. That means that 36 quantized conductance states have been observed, which is equivalent to the 5-bit conductance quantization. So this device can be used for the quantum memory applications, where one can actually stay at different quantum conductance quantum values, and one can store more amount of information. So apart from that, in the low resistance state, we also swept the voltage between 0.2 and 1.1 volt with a step of 0.01 volts. We could see 68 current states, which demonstrates a 6-bit memory device using the tantalum pentoxide device that we have developed. So in one go, we tried to show that at 36 quantized conductance states, it demonstrates the 5-bit conductance quantization, and in another go, we tried to demonstrate the 6-bit memory states. So the next point that I would like to emphasize in realizing the conductance quantization over here using the mechanically controlled brake junction device. So basically the mechanically controlled brake junction device, as I mentioned, like you have to push the flexible substrate so that the contact will break. You can fine tune the gap between the two electrodes with the piezo material. Okay, it all depends upon how well you can control the gap between the two electrodes. The important thing that we have realized here is we use the magnetostriction phenomena. As you know that when you have a ferromagnetic material, if you apply a magnetic field in one direction along the length of the sample, the increase in the length will be in the magnetic field applied direction. In the perpendicular direction, there will be shrinkage of the material. So this concept we have used to control the quantum point contacts. So this is the mechanically controlled break junction device. We try to push the flexible substrate and then try to maintain the gap between the two electrodes. It all depends upon how many number of atoms are in contact. Suppose if many number of atoms are in contact, your device will be in the high resistance state, and if a few atoms are in contact, your device will be in the low resistance state. If there is a finite gap between the two electrodes, you can realize the tunneling of the electrons. So if the gap between two electrodes is less than 5 nanometers, you can see the quantum mechanical tunneling. So this can be realized by observing the behavior of the conductance variation. If you have steps in the piezo voltage versus conductance, that means that you are in the conductance quantization regime. If you have exponential decay for the conductance, that means that you are in the tunneling regime. So for this purpose, we have used a famous material which is called as the Teflon D, the terbium, dysprosium and iron kind of material, which is having the large magnetostriction, because we wanted to control the conductance quantization and tunneling using the magnetic fields in a remote way. So we wanted to develop an atomic switch which can be controlled with the magnetic field. Okay. So for this purpose, we have used a Bridgman technique to develop this single crystal grain oriented sample. The orientation of the grains in this sample is in the direction of 110 direction, and up to 1500 ppm has been achieved in this material, magnetostriction values. So this is the kind of device that we have developed, and the brown color one which you see here, it is a phosphor bronze flexible substrate on which a wire has been kept that is made up of the terphenol D, and then both the ends of this wire is fixed with the strike-cast. The reason why we fixed with the strike-cast is that whatever changes that we see, we wanted to demonstrate that it is due to the magnetostriction phenomena. Otherwise, if we have a loose ends, the sample can also move due to the mechanical motion. Okay, we wanted to prove that the conductance quantization or the change in the conductance quantization, it is due to the magnetostriction effect. That's the reason why we tried to fix both the ends with the strike-cast. And a 4 probe measurement has been used for measuring the conductance. So this is the same image that we have obtained, and as you could see here, there is a breaking of the nano contacts, and then like this is the same image of the device that we have developed. So this is over here. Initially the device is at high conductance state. Is at high conductance state. That means that there is a finite contact between the two electrodes. Okay. Now when you try to apply magnetic field in the perpendicular direction, so what can happen is that the length change will be in this direction, and correspondingly there will be perpendicular shrinkage. As a result of this fact, the gap between the two electrodes has been increased, and as a result the device has gone to the low resistance state. So this we could able to repeat several times. That means that by the application of the magnetic field in the perpendicular direction, so we could able to go from the low resistance state to the high resistance state, so which can act like a switch. So the magnetic field atomic switch using the magnetostriction phenomena. So here the concept that we used is the magnetostriction phenomena. Okay. So as the uniaxial magnetostrict to strain is proportional to m square by ms square, we try to calculate, we try to measure the magnetization. Theoretically we calculated m square by ms square, and this value, the variation that exactly matches with the variation that we have observed using the conductance values. Okay. So there is a perfect correlation between the conductance variation and the calculated magnetostriction from the magnetization. Then we try to further map this variation at different temperatures like 10 Kelvin, 20 Kelvin and so on up to 70 Kelvin. What we could see is that we could able to see some hysteresis in the conductance values. Okay. The variation, yeah.
20 minutes.
Yeah, done. In 2-3 minutes I will finish. Yeah. So what we could see is that we could able to see a hysteresis for the conductance values. So to confirm the hysteresis, we also tried to do the magnetization, and in the magnetization also there is a hysteresis. That means that it is due to the domain wall pinning. Domain wall pinning, we could able to see the hysteresis for the conductance graph. Then we also tried to apply the magnetic field in the perpendicular direction and also in the parallel direction. We could see a distinct variation for the conductance values that we have observed, and which is in line with the theoretically calculated values from the magnetization. Then we tried to control this conductance quantization and the tunneling phenomena using the magnetic fields, and this is the mechanical control. That means with the piezo we try to control the conductance quantization, and then we also try to apply the magnetic field and try to control the conductance quantization and tunneling phenomena. So the tunneling actually varies linearly, like when you take the log graph, and with the piezo voltage the variation of the log G by G naught is linear. So now as you could see here, the magnetic fields that we need to apply is of the order of 1 Tesla. Practically it is not viable. Okay. So we wanted to demonstrate this at very low magnetic fields. So for this purpose we have chosen another material which is called as a galvanal material, the iron gallium material, which is having the large magnetostriction at lower magnetic fields. That means up to 300 ppm at a very few 100 Oersted magnetic field. So this we have prepared using the melt spin technique, and this is the kind of ribbons that we have developed. And this ribbon also, like using this ribbon also, we try to make the mechanically controlled brake junction device. Then we try to push this one with the piezo and motor, and then this is the kind of the switching behavior that we have observed in the galvanal based mechanically controlled brake junction device. Okay. So this also exactly matches with the uniaxially magnetostrict to strain lambda by lambda s graph, and there is a perfect correlation between the conductance values and the magnetization behavior that we have observed. Then we also try to do the training effect. That means that it is not that once we do the measurement and we stop it. We have done several cycles, and as you could see here with the cycle number, the variation in the magnetic field switching where the device goes from low conductance to high conductance, the variation is very small. It varies from 29 to 28.7, 0.3 Oersteds only, 0.3 millitesla only it changes. So this demonstrates the robustness of the conductance values that we have measured. Then apart from that, we also try to do the conductance switching. The conductance quantization has been observed with the piezo voltage, and the most probable conductance step that we have observed is 1 G naught and then 0.5 G naught using the statistical analysis. Then we also try to control this conductance using the piezo voltage and with the magnetic field as well. As you could see here, the blue curve is from the piezo voltage. Conductance quantization has been realized, and also the tunneling behavior has been observed. So both the things are seen in the similar graph. Even with the magnetic field variation also, by fine tuning the magnetic fields, we could able to see the conductance quantization and also the tunneling behavior in the device that we have developed. So with this I would like to conclude my talk. I believe that I tried to glimpse some of the results that we have obtained in the RRAM devices that we tried to develop using the tantalum pentoxide. We could able to see the conductance quantization in the device, and I tried to demonstrate a 5-bit conductance quantization and then a 6-bit current levels, that means 6-bit memory device. Then further I also tried to demonstrate the atomic switch that is developed using the mechanically controlled brake junction device using the magnetostriction phenomena. We also tried to control the conductance quantization using the piezo voltage. We could able to see very well defined conductance quantization, and further we also tried to see the tunneling behavior for the conductance. Then with the magnetic fields also we tried to show the conductance quantization and also the tunneling behavior. Okay, so with this I would like to acknowledge all the funding agencies, IIT Hyderabad, then SCRB, then DRDO, and my group PhD students without whom I am not in front of you. So I would like to acknowledge. We have very beautiful IIT Hyderabad campus. I request all of you to visit IIT Hyderabad. Thank you very much.
Thanks for the talk. So now we are open for questions from the audience.
So, sir, it was a nice talk. I have a question that how did you decide that it will be a 5-bit or 6-bit? How you calculate that bit?
So it depends upon how many number of states are there.
But
See, for instance,
states are like 36.
yeah, if you see here, see 5 bit means like 2 power 1. 2 power 1 means 1 bit. 2 power 2 means 4. If you have 4 states, that means it's 2 bit. If you have 5 bit, 32 states must be there.
Okay.
Yeah.
Minimum 32 will be there.
No, there can be more also. We could able to see only 32.
5 bit means minimum 32 bits. Will be
Only 32 bits. 6 bit means 2 power 6. 64 states must be there.
Okay.
Yeah.
Okay. Other questions?
Very nice talk, Surya. I was wondering in the tantalum oxide case, you have this multiple states. So what is the reason we have these states?
So because we have selected voltage in such a way that let me just explain you. Yeah, here, and if you see here, we swept the voltage from minus 0.5 to minus 3 volts with a step of 0.06 volts. Okay, so initially the device is at minus 0.5 volts, and we waited here for 29 cycles. We could see a plateau. Then we increased the voltage with a step of 0.06 volts, then another plateau, then further it is increased with 0.06 steps, and so on.
Yeah, that is fine. I'm just wondering about the mechanism, physics behind why, like in the case of, you know about domain walls,
Yeah.
there's a movement of domain.
Yeah.
In this case, what is driving this state?
So it depends upon how many number of channels are between the top electrode and the bottom electrode. So as you know that resistive random access memory primarily dominated by the oxygen defect based filaments. Okay, so we basically control how many number of oxygen defects are there between the top electrode and bottom electrode by controlling the voltage. That's the reason why you could see the well defined steps.
Okay.
Yeah.
Thank you. In this case, the pulse that you're applying, the height of the pulse is same or it is changing?
It is same. Pulse is same.
Okay. That's very good.
The pulse that we have applied is 0.5 microseconds for all the measurements.
Any other questions from the audience? If not, I have two small questions. So, what are the sizes of your devices and what temperature are you doing this measurement?
So these measurements are at room temperature.
So it's
This is at room temperature.
surprising that like you find these conductance steps.
Yeah. See, there are two different ways by which you can observe the conductance quantization. One is from the Landau levels by the application of the magnetic field. So here the concept is not from the Landau levels. So here the concept is from the point contact devices. So through the oxygen defects. So when we have tried to apply the voltage across the top electrode and bottom electrode, oxygen atoms will migrate. So wherever oxygen atom is not there, you will have oxygen defects. So these oxygen defects will form a channel from the top electrode to the bottom electrode, one dimensional channel. If you reverse the voltage, there will be rupturing of the filament. So basically what happens is you can control the gap between these oxygen defects by precisely controlling the voltage. Okay, so that's the reason why we could able to see these conductance steps. That too we observed this one. We observed at high resistance state.
And the area of this device?
The area of these devices is of the order of micrometer to millimeter. We try to use the shadow mask and try to do, and we can also do this one with the photolithography and then electron beam lithography as well. Yeah.
Okay. So I think if there are no other questions, then I thank Professor Narayana for this talk.
Yeah.